So far, so good. Here's my next question. That works for all of these which have a base e. What would happen if we change that base? Come on, y equals 2 to the x. Now, this is, strictly speaking, I think this is actually an exponential function as well. But like when we refer to the exponential function, we're really talking about this one here. Okay, so this kind of form here, if I have y equals to some other base, right, does this still work? What does this actually look like?
It looks pretty similar.
It looks pretty similar. And if I get this up on the screen, you can see it does look pretty familiar. Can you just jot this down for me first? So we're looking at like these different kind of exponential functions today. And hopefully if we get up to it, we can get up to logs and trig as well. All right, so we've got two functions here, yeah? We've got our exponential in the red, and we've got our 2 to the x in the blue. So with this one here, what we want to think about is, okay, what does the gradient mean, Harry, at the end of the day? Remind me, like the gradient is a term that we're talking about, and the derivative, like what's the relationship between that? Like there is, right? Because what did you say? How did you describe the gradient? How did you describe the gradient?
The gradient
Is can we be a bit more mathematical with that?
it's a line.
The steepness at any particular point. Now, when you're doing lines, it was easy to do because you just do rise over run because the gradient's constant. It's just a single number. It doesn't change. Whereas here, the steepness clearly changes depending on which point you're at. Okay, so we found that the gradient function for an exponential curve in this form can be found using this. And I guess my question was, what about 2 to the x? What about this blue curve here? And Matt realized, hey, this is actually pretty similar. So I wonder if there's like something similar about it. Just to show you very clearly, right? I'm going to get rid of this curve for a moment, the blue one. And if I graph the derivative of e to the x, can you see how, like, when you get rid of it, it's literally on top of the curve. It's saying it's actually the same curve. That's not normal, right? It's not. So now let's say what happens with 2 to the x if I do the derivative. What's your predictions?
Not the same. Not the same.
Why do you say not the same?
It's going to be a bit bigger.
Oh, what happened here? So there's the purple curve here. Right, it looks like it's kind of below, but notice how it's kind of the same shape, right? It's a similar shape, but it looks like it's just been changed slightly. What we're going to do is we're going to realize how this actually comes about. So here's our curve over here. And what we need to do is we need to try and think about this in terms of our exponential function over here and some logs. So how should we do this? This is how we'll do this. I want to think about another way I can write 2 in terms of my logs and exponentials. And we've learned that one of our log laws is if I have e to the power log base e of 2, that actually equals to 2 as well. Okay, so it's one of our log laws. How do I write this in terms of 2 to the x? What if I want to raise both sides to the power x? What's that going to look like now?
Raise what?
If I want to raise both sides to the power x.
So 2 to the x. Right.
So I want to raise this to the power x, yeah?
To the x.
What happens to this side over here? What happens when you have a power raised to another power?
Multiply.
Multiply them together, yeah? So we multiply these two together. Now, the reason why I've written this in this form, right, is because we actually know how to find the derivative of an exponential function, which this is, right? You can see how these two are the same curve. If you graph those on Desmos, right, they would be the same curve. So we can just differentiate this guy, right? We can write y as e to the x log base e of 2. And if I took the derivative, I'm keeping this the same, but I'm taking the derivative of this guy and putting it down. Now, x log e2, log base e of 2, well, yeah, because remember, this is just a constant. Yeah. And if you go back to over here, when you take the derivative of something with a constant there, this is like the second derivative, right? That would just become 2, right? Because we're decreasing the power by 1, that's just going to go away, become 1. So same thing over here. This is just a number in front of x because log base e of 2 is just a number. So when you take the derivative now, we get log base e of 2 e to the same thing. Okay? Yeah, it's not looking too nice though, but we can tidy it up a little bit, right? Well, this guy here, what was this guy equal to from the beginning? 2 to the x, right? That was all the way from back here. So we can write this as log base e of 2 times 2 to the x. And, sorry? You can write ln as well, yeah, both are acceptable. So I guess the takeaway is, hey, so what's like the rule that we can develop? Well, anytime you're trying to take the derivative of a exponential function with a different base, right, you're going to get the same function. But you need to remember how the curve was slightly shifted, or was like slightly, transformed? That's because it's being multiplied by this constant. And what is that constant? Well, it's the log base e of whatever base you had before. Right? So in fact, we can generalize this, and so we can say, all right, if I've got y equals to a to the x, the derivative of that, y dash, will be equal to log base of e of a times a to the x. That's our derivative of any kind of base. Jot that down for me. Pretty cool.